So here we have an impulse momentum question. It's got experimental design written all over it. Later in the problem, you'll be presented with a table of data which you'll be analyzing, and then subsequently coming up with stuff. But first, let me read the question. Each time I try to paraphrase the question, I get lost somewhat, but I'm going to read it anyway. A student sets up an experiment with a cart on a level horizontal track. There it is. The cart is attached with an elastic cord to a force sensor that is fixed in place on the left end of the track. A motion sensor is at the right end of the track, as shown in the figure above. The cart is given an initial speed of 2 meters per second and moves with a constant speed until the elastic cord exerts a force on the cart, which then it's going to subsequently return it back to the original position. The motion of the cart is measured with the motion sensor, and the force the elastic cord exerts on the cart is measured with the force sensor. Both sensors are set up so that the positive direction is to the left. The data recorded by both sensors are shown in the graphs of velocity as a function of time and force as a function of time below. So here's our velocity graph. It shows an initial speed of -2 meters per second. That's because we're moving toward the motion sensor. And then as we move away, just before we reach the end, we're going to reach a speed of 2 meters per second. The force graph shows a history of the stretch of the cord. Starts at 0, reaches the maximum, and then the cord returns to its natural length. All right, first question: calculate the mass m of the cart. Using the impulse and momentum relation, F delta T is the area under the graph, so that's what that represents. And that's equal to 1 Newton seconds. That's equal to the change in momentum, m delta V. So solving for m, we take the area of the graph and divide it by the change in velocity. So when I said velocity, so make sure you keep track of the direction of the speed. Okay, so 2 minus 2, not 2, excuse me, 2 minus and minus 2, that's 4. It's not 2 minus 2, 0. So 1 over 4, 0.25 kilograms is your mass of the cart. Okay, moving right along. For the time period from 0.5 seconds to 0.75 seconds, the force F, the elastic cord exerts on the cart, is given as a function of time t by the equation F equals A sine omega t, where A is 6.3 newtons and omega is 12.6 radians per second. Using the given equation, show that the area under the graph above is 1 Newton second. All right, so we're given a function, and to find the area, we have to use the second tool of calculus. So the integral of f sub t dt. On your equation sheet on the back, there is the integral of sine, which is minus cosine. Now, I believe it's of the form sine ax, and the integral of sine ax is minus 1 over a cosine ax. So you know the drill. The drill part is, it's easy to make that swap, but the drill is evaluating the integral, in this case from 0.5 to 0.75. Okay, and there you see it in all its glory. And the answer is pretty darn close to 1, 0.99 Newton seconds. Moving right along. The experiment is repeated using a different cord that exerts a larger average force on the cart. The cart starts and ends with the same speeds as those in the original experiment. Okay, I'm having a hard time following this description, but I believe we can answer this owing to the fact that the mass isn't going to change of the cart, and neither is the change in velocity. So if m and delta v don't change, then the area under the graph is not going to change. Okay, so so we're going to say equal. Part D, the elastic cord from the original experiment can be modeled as an ideal spring with force constant K. So an ideal spring suggests that Hooke's law, the restoring force equal to minus Kx. And if we apply the the definition of work due to a variable force, your solution will be 1/2 kx squared. Nonetheless, we're going to associate the energy stored in the elastic cord, and subsequently, once that energy is released, we're going to equate it with the change in kinetic energy, or the increase in kinetic energy, 1/2 mv squared. So solving for maximum length, stretch of the cord, we get the square root of mv naught squared over k, and it can be represented as v naught times the square root of m over k. All right, moving right along. Oh, here we are. The student performed several trials of the experiment. For the first trial, the cart is empty. In each succeeding trial, a block is added to the cart. In all trials, the cart has an initial speed of 2 meters per second to the right. The cart rebounds to the left with a speed of 2 meters per second. All right, kinetic energy to last potential to kinetic energy. And the maximum change in length of the elastic cord is measured. Here's my thinking out loud. How are they getting 2 meters per second each time, at least for the initial speed? Maybe there's a spring launcher system. Just thinking. Okay, the total mass m of the cart and the maximum change in length of the cord in each trial are recorded in the table below. All right, that's nice. There's some raw data. Notice what I did with the mass. I created a column of the square root of m. And here's the reason why. I'm going to go back to the original, or go back to the previous page, and maybe 2 pages. Okay. No, excuse me. Went back too far. Go back to this page. Notice that I have a relationship of x equals v naught square root of m over k. I'm anticipating they're going to set us up with x proportional to the square root of m. So in this case, I'm thinking, all right, change in x over change in the mass. And given the constant, what we think are constants, we have a initial speed and the spring constant. That's going to be equivalent to v naught over the square root of k. So eventually we're going to be solving for k. And with our slope and our initial speed, that should give us a reasonable value for the constant. And here are my choices. It was based on that. I just needed to explain it a little further. Kind of backtrack. Vertical axis will be your stretch, maximum stretch, and the horizontal axis will be the square root of the mass. Okay. All right. Let's plot the data. Now, I didn't plot it on the graph that you were given, but something pretty darn close. And although this is a previous work, let me erase this so you can see what I did here. Notice that the data points, when I plotted and then subsequently drew my line of fit, pretty close to the line. That's not that bad. So I choose 2 points on the line, not the data points. Remember, be really careful. And here are my coordinate pairs. So I have square root of m and x for my points earlier versus my points later, as they say. So the slope of that graph we obtained was 0.33 meters per square root of kilogram. And associating that with what's here in the denominator, given the initial speed 2, out pops 36.7 newtons per meter. Okay, there you have it. Use the best fit line to calculate the force constant K of the elastic cord. I'm a big fan of these problems. We have a lab experience, and I think it's fair to ask questions based on our lab experience and knowing our way around the lab and the equipment that's available to capture this data, or collect it, for that matter, traditionally, meter stick, stopwatch. All right, have a nice evening, or day for that matter.